Hi there, this is Heath. We're looking at section 12.6 in the book, which is cylinders and quadric surfaces. Let's go ahead and get started. In the previous section, we discovered the behavior of linear functions, the line and the plane, as they appear in 3 dimensions. A line had a vector equation, of the form x, y, z as a vector equals, and then some vector times t plus a starting position, and then another vector coordinate times t plus a starting position, plus another vector coordinate times t plus a starting position. Or what we call parametric equations, in which we just separate this out into 3 separate equations. X equals v1t plus a1, and y equals v2t plus a2, and z equals v3t plus a3. A plane has a single equation. Put it down here. Some number times x plus some number times y plus some number times z equals a constant, where a, b, c is a normal vector, and a normal vector is one which is orthogonal to the plane. So what we're going to look at this section are the quadratic functions. What happens if x or y or z or more than one of them is squared? So we're going to look at the quadratic functions in 3 dimensions. We know that in 2 dimensions, when you square something, you get a parabola. What happens in 3 dimensions? That's sort of the idea. All right, so let's look at our first shape, the cylinder. A cylinder is the graph in 3 dimensions generated by taking a 2-dimensional curve. In this case, our curve is this parabola down here, and translating it along a fixed line segment, in this case, a vertical line. So we're taking the graph of the parabola y equals x squared, translating it along the z-axis, and we get a 3-dimensional shape which looks like an infinite number of copies of this parabola stacked on top of each other. Every cross-section along the cylinder looks exactly the same. Okay? Why does this work? Well, let's take the equation that we have, y equals x squared, and pick a point where y actually does equal to x squared. So we're looking at the equation y equals x squared. We're looking at the point, and I'm just using this as an example, 2, 4, 1.3. And if we test this in the equation, well, y is 4 and x is 2, and that checks. And the fact that z is 1.3 doesn't change the fact that y equals x squared. Z could be 2.8, or it could be negative 0.7, or it could be, 10 million. Z could have any value, and this doesn't work. This equation still works. And so if we pick an equation in which z is missing, and we talked about this the very first day of class, if one of the variables is missing, then what we get is the 2-dimensional shape, and it's just repeated for every z value that we can possibly have, because the z value doesn't change the equation. And it doesn't matter if z is missing. If any variable is missing, we get a shape that is translated along that missing axis. Okay? Cylinders are commonly named for the shape at the base of the cylinder. So this particular example, since the base is a parabola, would be called a parabolic cylinder. We can also have an elliptic cylinder, a hyperbolic cylinder, and a circular cylinder, whose bases are ellipses and hyperbolas and circles. Any equation with only two variables is a cylinder in 3 dimensions, and it's translated along the coordinate axis that corresponds to the missing variable. Okay? So on the next slide, I think we're going to try an example. Yes. We're going to sketch this cylinder. 4y squared plus 9z squared equals 36. So one of the things that I notice is that x is missing. And so we're going to have a shape that lies in the yz plane. That's this plane here. And then that shape is going to get translated along the x direction. So let's figure out what this shape looks like. Both y and z are squared. So if this were just y squared plus z squared equals 36, that would be a circle with radius 6. But the fact that there are coefficients and they're not the same changes this from a circle to an ellipse. And we can figure out what the intercepts are. When y equals 0, then the equation is just 9z squared equals 36. So z squared is equal to 4, and so z is equal to plus or minus 2. And so the z-intercepts are at positive 2 and down here at negative 2. And then when, I'll do it down here, when z is equal to 0, we get 4y squared is equal to 36. So y squared is equal to 9. And so y is equal to plus or minus 3. All right, and so y is plus 3 or minus 3. And so we have in the yz plane an ellipse that goes around like so. And since x is missing, this ellipse can travel in the x direction forever, and we just get copies of that ellipse in the x direction. Send this back also. All right. Now, at this moment, I'm going to give you a little bit of motherly advice. This is not just calculus exercise. This is just being able to do better in later on sections in this course. Take a minute and draw this yourself. Pause the video if you have to. And the reason why I think it's good to go ahead and be able to draw this and not just watch me draw it is that when you get to the point where you have to set up an integral and you have to figure out where the bounds of the integral are, the better you are at being able to visualize what that shape looks like, the easier it will be to set up an integral in 3 dimensions. And so mimic what we did here is draw the flat 2-dimensional shape. Draw the lines parallel to the x-axis. They have to be parallel, that extend the ellipse, and then make a copy of the ellipse along those lines. Okay? So I'm going to show you a machine-generated version of this graph on the next slide. On the next slide after that. Since the variable x is missing, any cylinder can extend along the x-axis. And so we get this shape here. It's nice, easy when you have a machine graphing this for us. But let's walk through the steps again. Draw your axes. plot the y-intercepts and the z-intercepts. They were at +2 and -2 on the z-axis. So plot the intercepts. And they were at +3 and -3 on the z-axis. On the y-axis. And there are no x-intercepts because there's no x in the equation. Finish the 2D shape. So that's this ellipse here. I'm just drawing all this a second time, but walking you through the steps to be able to draw this yourself. I can't draw well, but I can draw well enough for a calculus class. I'm not going to win any art awards, but I do know what I'm doing, and that's what I'm hoping that you'll get from this. All right. Then we draw extending lines that are parallel to the x-axis. The x-axis is the one that's missing here. So we're going to draw an extending line from here. And notice that these are parallel. And then draw an extending line up here. An extending line up here. And this extending line is almost in the same place, and that's okay. And then pick points, pick a distance, and then extend this point here that distance. So if I go out this far, I want to figure out what that distance is, and then go out about the same distance over here. So this distance, and then from this point I'll go about that same distance, and then from this point I'll go about that same distance. And then connect those extended points. And now I can kind of see how this is going to turn into a cylinder. If I want to be fancy at this point, I can start shading around the side of the cylinder. So plot a second ellipse. At a fixed distance away. I'm kind of squeezing all of this in. But at that point, you can kind of start to see how this drawing is an approximation of the, fully accurate machine-generated drawing. All right. The better you are at being able to construct your own graphs of these surfaces, the easier it will be to visualize where the endpoints are and how to set up the boundaries, and you will have an easier time when you get to the integration chapter. And so this section is worth spending some time on. It's not, the math is not hard, but the drawing is hard. And if you have not done this before, spend some time getting good at it, okay? All right, let's try another example. Sketch this cylinder and identify it by name. Okay, so let's see if we can do what we just did before. This graph only extends in the x and y, only has an x and y in the equation, and so z is the missing variable this time. So we'll start out by drawing our axes. We'll figure out where the intercepts are. When x is 0, we get 4y squared equals 16. And so y squared is equal to 4, and so y is equal to plus or minus 2. And when y is equal to 0, x squared is equal to 16, and so x is equal to plus or minus 4. And so here are our intercepts, 2 and -2 on the y-axis, and 4 and -4 on the x-axis. All right. We'll connect these together to form an ellipse. Okay, I'm not drawing this ellipse very well. The long ones are hard to draw, hard to get the axis to go around for me. There we go. All right, that's not a very good ellipse, but that's a little bit better. I'll take out a little bit of this here. Okay, bad ellipse, but we'll move on. Then we draw extending lines in the z direction. So we'll go straight up from here. I have a problem with vertical. Let's try that again. There we go. An extending line from there. That's better. Turn my hand. And pick out some distance and then go that distance up from each of these points. And then connect these points together also to make a second cylinder. And we can kind of see now the shape that we're getting here. It's a elliptic cylinder that goes around the XY plane and up in the Z direction. Okay? Again, this is a terrible drawing. It will not win any kind of art awards, but it does help me visualize the orientation position of the shape. Okay? And I hope that you can draw it at least that well. If not better. Hopefully better. There are two other practice problems that I'm not going to work through here, but if you want to work through them and talk about them through office hours, I am happy to be around and answer your questions, okay? All right. So let's move on. What if all three variables are present? Then we don't have a cylinder anymore. We're looking at something else. This is called a quadric surface. A quadric surface is the graph of a second-degree equation in 3 dimensions. To sketch a quadric surface, we're going to make extensive use of what are called the traces of the surface. A trace is a cross-section that's parallel to one of the coordinate planes, parallel to the xy plane or the yz plane or the xz plane. The equations for traces you find by taking one of the variables and make it into a constant. Often it's 0. There's nothing wrong with using the trace at x equals 0 and y equals 0 and z equals 0, but you're allowed to use any constant you want to generate the trace. So let's try this example. We want to sketch this quadric surface. The equation is x squared plus y squared over 16 plus z squared over 9 equals 1. All right. Oh, so let's see what happens. We'll start by creating the traces. So if we set z equals 0, this is a trace. So that's the first thing we're doing. We're creating the traces. I will later on do y equals 0 and x equals 0, but we're doing z equals 0 first. We get this equation, x squared plus y squared over 16 is 1. And that's this ellipse shown here. The intercepts are at y equals 4 and at x equals 1. So we go 4 units out on the y-axis and negative 4 units out on the y-axis, and 1 unit and negative 1 unit in the x direction. So that's what the trace looks like here. Okay? If we set y equals 0 and we set x equals 0, we also get ellipses. Let's draw all 3 traces now. We created the traces. We're going to draw all 3 traces. The one that was on the previous slide had intercepts at 1 and -1 on the x-axis, and at 4 and -4 on the y-axis. And so when we connected them like so, we got this sort of long, skinny ellipse. So now let's look at this trace. This goes through the x-axis and the z-axis. The intercept in the x direction is plus and minus 1, which is right here and right here. The intercept in the z direction is at plus and minus 3. So we go up 3 and down 3. And we connect those together to form an ellipse. Okay, and again, that's not a very good ellipse. That's fine. Then if we set x equals 0, we get y squared over 16 plus z squared over 9 equals 1. This has intercepts at plus or minus 4 on the y-axis and plus or minus 3 on the z-axis. And so now we connect an ellipse through those 4 points. And if you look at these 3 traces, now you have a pretty good idea of what the shape looks like. The shape looks like not quite a sphere because it's longer in one direction and skinnier in one direction, but it's got elliptical cross sections in all 3 directions. And so we get this shape here. 4 units out in the y direction, 3 units up and down in the z direction, and 1 unit forward and backwards in the x direction. All of the cross sections are ellipses, and we have this sort of roundish, but it's a squashed sphere-looking shape. The name for this shape is an ellipsoid. 2 dimensions, we have an ellipse. 3 dimensions, we have what's called an ellipsoid. It has cross sections whose shapes are ellipses. Okay? All right. So let's try another example. Let's keep going. Let's sketch this surface. Z equals x squared over 2 plus 3y squared. Now, in this example, the z is not squared. I want to go back to the previous example for just a moment and show that in the previous example, all 3 variables were squared. In this example, one of the variables is not squared. Okay, so let's do what we did before. Let's start with the traces. So let's look at the trace z equals x squared over 2. That's if we set y equal to 0. If we set x equal to 0, let's do that one next. We get z equals 3y squared. And if we set z equal to 0, we get 0 equals x squared over 2 plus 3y squared. I want to talk about these 2 first. When one variable is squared and one variable is not, these are parabolas. Just like y equals x squared was a parabola in 2 dimensions, z equals x squared is a parabola in 3 dimensions, z equals y squared is a parabola in 3 dimensions. So let's look at what's going on here so far. We have x and y and z. This is a parabola that opens up in the zx plane. And this is a parabola that opens up in the zy plane. But the fact that this is 1/2 x squared and this is 3y squared that coefficient in front of the squared term changes how wide or how narrow the parabola is. And so this is a parabola that's going to be fairly wide in the x direction and fairly narrow in the y direction. So in the y direction, when y is equal to 1, z is equal to 3 times 1 squared. And when y is negative 1, z is equal to 3. And so we're going to have, kind of a tall, skinny parabola. On the other hand, when x is 1, z is only 1/2. And when x is negative 1, z is 1/2. In fact, when x is 2, z is only 2. 2 squared over 2 is 2. And z squared over 2 is 2. And so we have a much wider parabola going on in the zx direction, okay? Are you seeing that? And so we have a parabola opening in both directions. Let's talk about this direction here for a moment. This looks like an ellipse, but the 0 constrains the radius of the ellipse. If we look at the intercepts, x squared over 2 equals 0, and 3y squared over 2 equals 0, then we get x equals 0 and y equals 0. It's an ellipse with a radius of 0. There's no point. Or there's only a point. The radius is 0, so that's just a dot in the xy plane. So those are our traces. A parabola opening up this way, a parabola opening up this way, and a dot at the base. And so if we connect these up, we get a shape that looks kind of like a bowl that opens up and keeps going on forever. Let's walk through the steps here. The traces through x equals 0 and y equals 0 are z equals 3y squared and z equals x squared over 2. Both of these traces are parabolas. That's what we did here. But the trace through z equals 0 is this equation, and it's only a single point. It is an ellipse of radius 0, which is just a single point. Doesn't give us much information about the shape. But if we change z to other values, for z being greater than 0, this is an ellipse, and that c, now that is not 0, will be a radius. And so all of the cross-sections above z equals 0, those cross-sections are ellipses. And that's what these shapes are up here. Okay? And so we have a dot at the base, parabolas going up the sides, a wider parabola in the x direction than we have in the y direction, and ellipses going through if we rise up above the dot for values of z that are greater than 0. And then you get this shape. All right. If we think about the cross sections that we have parabolas and ellipses, but we have parabolas in the x direction and the y direction, and ellipses only in the z direction. And so parabolas are 2 of its 3 traces. The trace through x equals 0 and y equals 0. 2 of them are parabolas, and the only other one was different. So we had mostly parabolas. The majority, 2 out of 3, were parabolas. And so we named this for the shape that has the majority of its traces. It's a paraboloid because it's mostly parabolas for the traces. And the third trace is an ellipse. So we call it an elliptic paraboloid if we have to identify that third trace. Okay? There's another kind of paraboloid, we'll see that in a moment, called the hyperbolic paraboloid, where 2 of the traces are parabolas. One is a parabola that opens upwards in one direction, and one is a parabola that opens downwards in one direction. And then the other traces are hyperbolas. If I were to slice through, let's say, z equals 1, I'd get a hyperbola with these two little pieces. A little piece up here and a little piece down here. Or if I were to slice down through the bottom, I would get a little piece down here and a little piece over here. And that creates that hyperbola shape. Of the two little shapes that open away from each other. Okay? This is a tricky shape to draw. What I tend to do is take the boundary on one end. This is a parabola opening up. And then this over here is a parabola opening up. And draw those first. And then in between those are parabolas opening down for the other two sides. And so draw a parabola opening down for that as well. And then I tend to probably draw an extra parabola going across the middle. And that's not a perfect drawing, but it's a pretty close drawing of this shape, is to focus on like what the what's going on around the origin. It's kind of a box with two parabolas opening upwards this way and two opening downwards that way. Okay? All right. The next shape doesn't fit our naming terms. We've talked about ellipsoids and paraboloids. This was a cone. Some people call it a double cone because there's the upward part and the downward part. Our book just calls this a cone. It has a z squared in the equation. This is a very simple cone. Z squared equals x squared plus y squared. And because the z is squared, when we solve for z, we get a positive and a negative value. And so we get the positive cone and we get the negative cone from the equation. And so that's where the doubled version of the cone comes from, is that the z is squared in the equation. Okay? The important thing here is that there is no constant term in this equation. And so what happens is when I start to look at the traces, my traces are, if I leave out x, say x equals 0, I get z squared equals y squared. If I look at y equals 0, I get z squared equals x squared. And if I look at z equals 0, I get 0 equals x squared plus y squared. Z squared equals y squared, because both sides are squared, I could take the square root of both sides, and I just get z equals plus or minus y. And so these are two lines. Z equals y has a slope of 1, and z equals minus y has a slope of negative 1. And so we have a line with a slope of positive 1 and a line with a slope of negative 1. And those are the sides of the cone. Same thing in the x direction. We have a slope line with going in the x direction with a slope of 1, and then a line in the x direction with a slope of negative 1. And then the z direction, x squared plus y squared equals 0. That 0 again, that's why there's no constant term here. That gives me a circle of radius 0, or an ellipse of radius 0. This is x squared plus y squared equals r squared, and r is 0 in this case. And that's the dot right there at the center of the cone where the x and y axes meet. And so a double cone has all three variables squared, but there is no constant term in this equation. That's going to be important. If we back up, way back up to example 2, or example 3, I'm going in the wrong direction, sorry. Example 2, there was a constant term in this equation. So we didn't get a cone, we got an ellipsoid. This equation doesn't have a constant term. That's sort of the thing that identifies a cone. The other two shapes we are the hyperboloid of one sheet. Now we've seen this structure before. In 2 dimensions we have a hyperbola. In 3 dimensions we have a hyperboloid. A hyperbola in 2 dimensions is this shape that turns away from each other. It has 2 curves that sort of turn away from each other. And we can see that here that they are turning away in the x direction and they're turning away in the y direction also. But where they cross, there is they're connected in the middle. There's like a little waist in the middle, inside this sort of torso-shaped object. If they're connected in the middle, there's just a single piece to this hyperboloid. Even though an individual hyperbola has 2 pieces, all of this shape is connected, and so it's just one sheet. The other possibility is what we call the hyperboloid of 2 sheets, where we have a hyperbola in the y direction and a hyperbola in the x direction. They open away from each other, but there is nothing in the middle. That the radius all the way in the center turns out to be the square root of a negative number. And that's imaginary, so there is no radius in the center. And if there is no positive radius in the center of the shape, that separates the shape into 2 parts, and then it's called the hyperboloid of 2 sheets. They're both hyperboloids. The cross sections in both cases are hyperbolas. The question is, what's the radius of the section in between the hyperbolas? And we'll do an example of this in a moment also. All right. But those are the 4 possible shapes that we can get in 3 dimensions. Summarizing what we found, we could have an ellipsoid. We can have a paraboloid. And there are 2 kinds of paraboloids, elliptic and hyperbolic. We can have a cone, that's the one that doesn't fit our naming scheme. And we can have a hyperboloid. And there are 2 kinds of those, 1 sheet and 2 sheets. Okay? So if I give you an equation, how can you tell from looking at the equation which of these shapes we get? To help recognize a quadric surface without having to sketch traces, I recommend that you learn how to sketch these. I do want you to be able to draw them, but if you are working through a time test and you have to do this quickly, there is a standard form where we are going to put the squared terms together on one side of the equation. Some of the exponents may not be present. We saw, for example, in the paraboloid that z was not squared, and so the exponents may be missing from the equations. These terms may be 0. When we complete the square, we may get a 0 there. That's okay. And then the constant term will either be present or 0. Now, if it's anything other than 1, like if it's a 7, we can make it into 1 just by dividing both equations by 7, and that's going to put some things in the denominators over here. That's the idea. So any number that's non-zero, we divide by that number, and that gives us some denominators over here. And then we end up with a 1 on the right side. So the right side will either be 0 or 1. We will divide by the right side to make it a 1, unless the right side's a 0 and we can't divide by 0. We're stuck with a 0 there. Okay? Are we okay so far? So let's try putting an equation into standard form. X squared plus z squared minus 6x minus y plus 10 equals 0. Okay? So, sorry, let me work through this. So I'm going to group the variables together and put the constant on the other side. So x squared minus 6x minus y plus 2z squared equals to negative 10. So group variables. Group like variables, let's put it that way. And then move the constant to the right. This has an x squared and an x term, and so I'm going to try to complete the square for this term. Complete squares if needed. So to complete this square, x squared minus 6x, I'm going to have to add a plus 9. That's take the middle, this term, divide it by 2 and square it. So negative 6 divided by 2 is negative 3. Negative 3 squared is plus 9. So I'm going to add a plus 9 over onto this side also. And then that gives me x minus 3 squared minus y plus 2z squared equals to negative 1. All right, but we want the constant term to either be 0 or positive 1. So I'm going to get rid of the negative sign by dividing by negative 1. So the constant is equal to 1. And so this will give me negative x minus 3 squared plus y minus 2z squared equals to 1. And this is standard form. Okay. Group like variables together, complete a square if you have to. And then once the square is completed, see if your constant is 0 or something else. If it's something else, make it into a 1. Okay. Once we have the standard form, we have what's called a decision tree that will tell you the shape of the form. It's 5 questions long. You will want to memorize this decision tree. It's just faster than having to look it up, and you won't have it for the final. But let's look at the decision tree here. First question, are all 3 variables present? If the answer is yes, we're going to move on to the next question. But if no, we know that if one of the variables is missing, the graph is a cylinder. And it's a cylinder that will extend along the axis that's a missing variable. That's what we did at the beginning of today's class. So check for that first. Are all 3 variables present? If the answer is no, we have a cylinder and we can stop. We have made our decision. Is only one of the 3 variables squared? For example, all 3 variables are present, but we only have one squared variable. If the answer is yes, the graph is still a cylinder, but it's a diagonal cylinder. Okay? Kind of like this. And I'm going to go ahead and tell you we're not going to cover diagonal cylinders in this class. So I want to fill this step in, but we won't cover these. What are called oblique cylinders. So you don't have to worry about being able to draw an oblique cylinder for this class. Only the ones that are straight along one of the axes, not a diagonal axis. Okay. We do cover oblique cylinders later on. If you want to take the next class after this in the calculus sequence, it's 3214. That's the course number. But most of you will not be required to take that course. Okay? All right. So if the answer is no, and for this class the answer will be no, we'll go on to the next question. So check to see if a variable is missing. And if the answer is no, we stop. It's a cylinder. And if the answer, all three variables are present, check to see if all three variables are present. If there's a missing variable, we have a cylinder. If all three variables are present, we go on. Is only one of the variables squared? That's the indicator for an oblique cylinder. We won't cover oblique cylinders, but at least you know how to recognize them. Otherwise, we go on to the next question. Are only two variables squared? And we did this example earlier, where we did z equals x squared over 16 plus y squared, I think was the example we did. That's x squared over 9 plus 3y squared. This was the example we did earlier. Except it was x squared over 2 plus 3y squared. Something like that. We did an example like this before. That gave us, because the z was not squared, z equals x squared was a parabola that opens up in the z direction, and z equals y squared is a parabola that opens up in the z direction. If only two of the variables are squared, we have a paraboloid. It's elliptic if the squared terms have the same sign. It's hyperbolic if the squared terms have opposite signs. So that is how we recognize a paraboloid. If only if more than two of the variables are squared, we go on to the next question. So we have checked for one variable being squared. We've checked for two variables squared. Now we know all three variables are squared. So we check to see if the constant term is 0. And if the constant term is 0, the graph is a cone. Okay? Flat out, it's a cone. There's one weird special case if all three terms have the same sign. So if we have x squared plus y squared plus z squared equals 0, or negative x squared minus y squared minus z squared equals 0. This is the special case that we only have a single point, that it's a cone that's failed to open. It's called a degenerate cone. That's a funny name because, degenerate comes from that. But it means it did not generate anything. Nothing got generated, just a single point, degenerated. If the terms do not all have the same sign, if two of them are negative and one's positive, or two of them are positive and one's negative, the cone will open in the direction of the variable whose sign is different from the other two. So if I have x squared minus y squared plus z squared equals 0, the y is the one that has a different sign, and so it's a cone that will open along the y-axis. It opens along this variable whose sign is different from the other two. All right. So now we're at the last question of the decision tree. We know that all three variables are squared and the constant term is not 0. How many of the squared terms are negative? If none of them are negative, we have an ellipsoid. If one is negative, it's a hyperboloid with one sheet. And if two are negative, it's a hyperboloid with two sheets. In both cases, it opens in the direction of the sign that's different from the other two. When only one term is negative, we have one negative and two positives, and the one negative determines the direction that it opens. When there are two negatives, we have two negatives and one positive, and the one positive denotes the direction that the hyperboloid opens. So in both cases, the hyperboloid opens in the direction of whichever variable has a different sign from the other two. If all three square terms are negative, the graph is the empty set. We don't really have to worry about this case, but I'll talk about what happens if we have a negative x squared term and a negative y squared term and a negative z squared term, and the constant is not 0. Remember, we said the constant was not 0, so in standard form it's 1. I can't have a negative term plus a negative term plus a negative term add up to positive 1. This can't happen. And so if we ever see this, that's an impossible equation. There are no points that satisfy it. The graph is an empty set. You don't worry about that. That's going to be a peculiar case, but it completes the decision tree. Okay? So 5 questions. They're easy questions once you have standard form. Just look at the standard form and go through this. Okay? If you check in the notes, in the PDF notes, I have this decision tree in the form of a flowchart. I did not reproduce the flowchart on the slides here because it's a little hard to read. It was kind of cramped on the slide, and so I didn't reproduce it here. But the decision tree is also in the PDF notes in the form of a flowchart, and that may make it easier to help remember the order of the questions that we go through this. But if you understand that decision tree, you can name these shapes pretty quickly. You get pretty good at this. All right. So let's try using that decision tree to identify the graph of this equation. Okay. So first thing we have to do, this is not in standard form. So we have to put it in standard form first. Okay? So if we put this in standard form first, we group the variables together. So on the left side, we're going to get 2x squared minus 16x. I'm bringing this 16x over here. Minus 4y squared plus z squared equals to negative 8. So the z squared came over here and became positive, but the negative 8 stayed on the right side. I have an x squared and an x, so we're going to have to complete a square. And there's a 2 in front of here. That complicates things a little bit. This is now x squared minus 8x inside parentheses, minus 4y squared plus z squared equals to negative 8. To complete the square, take the negative 8, divide it by 2. That gives me a negative 4. Negative 4 squared is plus 16. But this is really 2 plus 16. And so we have to add 32 to this side because it's 2 copies of 16. And so that gives me 2 times x minus 4 squared minus 4y squared plus z squared is equal to positive 24. The constant term is not a 0, so we're going to divide by 24 and make the constant term equal to a 1. So we get x minus 4 squared over 12, the 2 and the 24 reduce, minus y squared over 6, the 4 and the 24 reduce, plus z squared over 24 is equal to 1. Okay? That's our standard form. And now we go through the 5 questions from the decision tree. I'm hoping that you have your notes in front of you that has the 5 questions in here. Is there a variable missing? And the answer is no. Okay, so if a variable isn't missing, is only one variable squared? And the answer is no, all three of them are squared. Then the third question is, are two variables squared? And the answer is still no. The fourth question is the constant term 0? And the answer is no, the constant term is 1 in this case. And the last question is, how many squared terms are negative? And the answer to that is 1. The y squared term is negative. And if you remember, the outcome of the decision tree is one negative sign means it's a hyperboloid of one sheet. And so this is a hyperboloid of one sheet. And it opens along the y direction. And so it's going to kind of have this shape to it. If we want to graph it a little bit more carefully, we could plot some intercepts and try to get that shape narrowed down, but that's the general idea. It's going to be this hyperboloid of one sheet that curves inwards as the hyperbolas come inwards and then goes outwards towards infinity, but along the y direction. Okay? So we'll go through these steps here. We rewrite the equation in standard form. All three variables are present. All of them are squared. Only one of the coefficients is negative. Those were the parts for the decision tree. And so the surface is a hyperboloid of one sheet. Okay? All right. There's some practice questions at the end. I'm going to do one of them with you, and I'm going to leave you to do the other ones. Let's sketch the graph of this equation and identify it by name. Okay? So this is not in standard form yet. But this is pretty easy to put in standard form. If I put 4x squared plus 4y squared minus z squared equals 0, now it's in standard form. There are no squares to complete, and the constant term is 0, so there's nothing to divide. That's standard form. Oh, that was kind of a letdown because there's no work to do, really. But you should recognize now, if you remember the decision tree, all of the variables are present and all of them are squared, but the constant term is 0, and that makes this a cone. All right. So let's talk about how we would graph this cone. Let's look at the traces. Again, traces are what we get when we eliminate one variable at a time. When we set x equal to 0, then we are looking at 4y squared minus z squared equals 0. That's the same thing as 4y squared equals z squared. And so if we take the square root on both sides, plus or minus 2y equals z. So in the zy plane, when y is 1, z is plus 2 or minus 2. When y is 2, z is plus 4 or minus 4. And so we have a pair of lines in the zy plane. This line with a slope of positive 2 and a line with a slope of negative 2. So then let's look in the y plane. Y equals 0 trace. That's in the xz plane, sorry. And that's going to be 4x squared plus 0 minus z squared equals 0. Well, that's the same thing. 4x squared equals z squared. Take the square root on both sides. And plus or minus 2x is equal to z. So when x is 1, z is equal to 2. When x is 2, z is equal to 4, or negative 2, or negative 4. And so we get lines in the xz plane as well. So then let's look at what happens when z is equal to 0. When z is equal to 0, we get 4x squared plus 4y squared equals 0. That's just a dot at the very center. It's an ellipse with a radius of 0. But when z is greater than 0, not equals, we get 4x squared plus 4y squared equals some constant now, some positive number, and then x squared plus y squared is equal to that number over 4, and so it will be a circle whose radius is the square root of this number. And so if z is positive, we get circles, and actually if z is negative, we still get circles because z gets squared. And so we get a cone shape that opens in the z direction. Okay? All right. Take some time, work through the other sketches, get in touch with me if you have questions about them. We'll talk about them over office hours. Thanks for coming. Have an excellent weekend, okay? All right.